How many of you in the room are taking Comp Arc this semester from Chris Batten? Now that's a good time, isn't it? It's serious good time. It's like boot camp. You are the few, the proud. He is an exceptional teacher, in my humble opinion, having sat in on a couple of his classes. So. Okay, any other questions about anything?
Speaking of classes,
is there a sequel to this class? This is an interesting question. This class is a prerequisite for a number of upper-level ECE classes. The most natural immediate sequel is unfortunately not happening next spring because the professor teaches it and is on leave. That's DSP ECE 4250. However, this does lead into digital communications taught by Professor Wagner. That's an excellent class. If you've also taken 3100, that's something you're eligible for. That's one I can think of right off the top of my head. And it's the only one I can think of right off the top of my head, but I'm sure there are others. So, yeah, when is the junior pre-reg dates? Oh, so it's not for a while. Yeah, okay. Any other questions? Okay, well today what I want to do is finish up talking about the Fourier Transform stuff, and then I'm hoping to start the couple of lectures on wavelets, kind of scratching the surface of that, which is something I've never talked about in class, so it's going to be a new adventure for me. And I've tried to plan for it, but we'll see. We'll see how it goes. Anyway, we're talking about the Fourier Transform, and essentially we're talking about loose ends. And last time we talked about the general idea of how Fourier transforms play into analyzing LTI systems. So if you've got an LTI system that has a frequency response, the frequency response of that system is h hat, which is the Fourier transform of the system's impulse response. This is another way of looking at frequency response for LTI systems. We had an original definition. The frequency response's value at omega is what you multiply e to the j omega t when you put e to the j omega t as the input to get the output signal. Now we have another way of looking at it, is the Fourier transform of the impulse response. And we have these two important things that I like to keep separate in my head, but you can actually reconcile them if you play with the deltas appropriately. So two important pictures for such a system. So this is for a linear time invariant system. If you put the input x of t equals e to the j omega, say, well, just leave it omega t, into the system. So this is for all t. What comes out is output signal s of x, whose specification is h hat of omega, e to the j omega t, for all t. That's one picture. That's how the frequency response plays into the way the system responds to pure sinusoids. If you put in an input signal that's not a pure sinusoid but has a Fourier transform, so if x has Fourier transform x hat and x is in d sub h, in other words, it's an admissible input to the system, it's convolvable with the input response, then if you put x of t into the system, you get s of x as an output, and s of x is going to have Fourier transform h hat x hat. So this is how the system operates on pure sinusoids. This is how it operates on general inputs. And in each case, we can think of the system as reshaping the frequency of the content of the input to give you the frequency content of the output. And we talked about ideal filters, because this view of systems that have frequency responses, allows us to characterize any such system as a frequency selective filter. So we talked about ideal filters, ideal low pass, high pass, and band pass filters. These are things you've seen before, at least in discrete time, in EC 2200. And these things are you can't build them because they're not causal. You can only approximate them. And the first part of today, what I want to do is I want to talk about one way of approximating frequency response magnitude that you wish you could realize just as a magnitude with no phase. And then I want to talk about one way of circumventing a situation where in real life you're actually stuck with a filter. And we talked about this last spring in EC 2200 a certain amount. I'm going to do it a little bit differently, I think, now, but it'll look somewhat familiar to those of you who were there. Okay, so the key thing about this, the key thing that makes these not causal, turns out to be a lack of phase. Their frequency responses are real valued. In fact, they're non-negative, so equal to their magnitudes. So the frequency responses are real valued and, in fact, for each of these ideal filters, the frequency response value at omega is equal to the magnitude of the frequency response at omega, for all omega. It's possible for something to be real valued but have this not be true. All it has to be is negative for some values of omega. Then you would have a phase of plus or minus pi. But the basic thing, it turns out, that makes these things non-causal is a lack of phase. It turns out that if you take any causal system, its impulse response is going to be 0 for t less than 0. And you can prove mathematically, and I do this in the monograph, that the frequency response of such a system is going to have non-trivial phase. Okay, so a typical filter design problem in real life is trying to design a filter that is pretty much like one of these ideal filters. It's pretty much like an ideal low pass, pretty much like an ideal high pass, or pretty much like an ideal band pass. And really, once you've done the low pass, you can get the others very easily from that. So I'm just going to look at that one. So here's a sort of a typical filter design problem. And it goes like this. You're given some desired frequency response magnitude. And I'm going to call it h hat desired of omega with magnitude signs around it just to emphasize that it is a magnitude. And your goal is want to design a causal filter with frequency response h hat desired, yeah. Oh, by the way, why are you all dressed up today?
Oh, I'll have an interview.
Interview with whom? Schlumberger?
Yeah.
Energy sector?
I don't know why, but...
You know what? Schlumberger likes to hire people who know signals and systems, because a lot of what they do is listen to the ground. You know, they say, where's the oil? You know. Yeah, and so they use wavelets, actually. They use a lot of wavelet analysis for their seismic stuff. Anyway, just don't say Schlumberger. Yeah. All right, so anyway, has frequency response h hat satisfying the following two criteria. H hat magnitude is roughly equal to the desired magnitude. And the phase of h hat is not too bad, whatever that means. Not too damaging. Okay, so what does not too damaging mean in terms of phase? So question, what is quote unquote not too bad? First, a little aside. Notice that if you are only going to be forcing your system with pure sinusoids, phase isn't a problem. It's only a problem when you're forcing it with inputs that have a spread out spectrum. Why is that the case? So note first that if you're forcing the system only with pure sinusoids, then phase is not a huge problem. Now, why is that? Here's the basic idea. If you take, and I'm going to be casual about the notation here, if you take e to the j omega 0 t and you put it into the system, what's going to come out? What's going to come out is h hat of omega 0, e to the j omega 0 t. And if you write h hat of omega 0 in polar form, exhibiting its magnitude and phase, you're going to get magnitude of h hat of omega 0 times e to the j phi of omega 0 times e to the j omega 0 t. And that in turn is equal to magnitude of h hat of omega 0 times e to the j omega 0 parentheses t minus t1, where t1 is equal to minus phi of omega 0 over omega 0. What this means is that if you're forcing the system with a pure complex exponential like that, what comes out is the same as just a time-shifted version of the output that would have come out had you had no phase associated with a frequency response. So that is to say, the output is just a T1 shifted version of what would have come out. So the output that would have arisen would have emerged if h hat of omega 0 had no phase, namely if h hat of omega 0 was just equal to its magnitude. And having a time delay is not such a bad thing. You know, you just say, okay, well, you know, the phase doesn't do too much damage. All it does is it shifts the output. I'll just wait, and that'll be what I get. And it'll be sort of like what would happen if I had no phase. The problem with phase arises, as I said earlier, when you have signals x, using signals x as input whose frequency spectrum is spread out over all omega. So phase is damaging for more general inputs. So for inputs x corresponding to Fourier transforms x hat, where x hat is quote unquote spread out over a range of frequencies. And I guess the location of the quotes is probably better after spread out. Because what happens then is that different quote unquote frequency components of x get time shifted by different amounts. And so the whole thing that comes out is a mess, and it bears very little relationship to what would have come out had you put x just through this frequency response magnitude. So the phase causes issues here. because the different quote-unquote frequency components of x get shifted, time shifted, by different amounts. Okay, so original question is, what makes a phase characteristic not too bad? And it turns out that if h hat of omega has what's called linear phase, then this whole situation boils down to essentially the situation we had with the pure sinusoids. So one example of a quote-unquote not too bad phase is linear phase. What does that mean? We say that h hat has linear phase when there exists, and I'm going to put signs on this, SIGNs, because it's something, I want to make sure it's causal, exists a T1 bigger than 0, such that h hat of omega is equal to the magnitude of h hat of omega times e to the minus j omega t1 for all omega. And from this formula, it's pretty obvious why we call that linear phase, right? The phase being the thing up here that's multiplying the j depends linearly on omega. Okay, now why is that not such a bad thing? Let's go back to our original filter design problem. We have a desired magnitude. H desired hat. Suppose we're able to design a causal system that has that desired magnitude with linear phase. So suppose we have h hat desired of omega and are able to build a filter with frequency response specified by h hat of omega equals the desired magnitude times linear phase for some T1. Note that the magnitude of that frequency response equals h hat desired. So observe, magnitude of h hat equals magnitude of h hat desired. So magnitude-wise, this is doing what we want it to do. It's boosting some, attenuating other frequencies in the input. What kind of damage does the phase term cause? Let's see. First, let's see what would happen if we were to put an input signal x into the desired frequency response, the one we can't build. So say we're given x, and x has Fourier transform x hat, right? And you use x as the input. And let's use it first as the input to the desired frequency response. So the ideal system, x is going to go in there. and an output is going to come out, and that output is going to have Fourier transform desired magnitude of h hat times x hat. The linear phase system, if you put x in there, s of x that comes out, let's call this one s desired of x, the one that would come out if we put it through the ideal system. And the one that comes out of the linear phase system, let's just call it s of x, that's going to have Fourier transform, magnitude of h hat desired of omega, times e to the minus j omega t1 times x hat of omega. And that's just equal to this thing times e to the minus j omega t1. Now, one of our operational rules for Fourier transforms tells us how the signal s desired of x and the signal s of x are related. S desired of x has this Fourier transform. S of x has this Fourier transform. So how are s of x and s desired of x related? Do you remember the rule, the Fourier transform rule that tells you, that introduces a factor like that? Come on, Victor, I know you know it.
I can't remember if it's minus or plus.
It's minus. Which one is it?
The frequency, no, the time.
Yeah. Very good. By the time shift rule, and Alex, I know you're going to say that, but I wanted to get one of the deeper rows for one. Okay. And Ricardo, you might have even known that. Haha. No. Does he actually watch? Do you know if he watches the videos when?
I don't know, I guess.
Okay, tell him to watch this one. So we'll give him a hard time for the whole. We have plenty of time left. Okay, so by the time shift rule, the actual output you get is just going to be shift T1 of the desired one. And this did not hinge on any assumptions about x being a pure sinusoid. This is any old x has a Fourier transform x hat. Thus, all this does is introduce a time shift. Linear phase just introduces a time shift. So that's the moral of the story. Linear phase just introduces a time shift, even for arbitrary inputs. Not just pure sinusoids. So what you'll find when you read like classic signal processing texts and everything, take courses that talk about filter design, even work for a company that designs filters, they say, well, we want a linear phase system whose frequency response magnitude is about equal to this. Design it for me. And so you have to figure out how to do that. All right, so that's one thing. That's filter design. You're trying to build something that performs in a certain way. And that's sort of the positive side of filters. So this is an example of designing a filter to perform up to some specifications. of one kind or another. Okay, so your goal is to make a thing, make a system that does something you want it to do. The other side of filters, the bad side, is circumventing filters that you encounter in the real world that you're just stuck with. So the sort of the other side of filters is designing schemes to circumvent or mitigate, or whatever word you want to use, the undesirable effects of filters that you have no control over designing. You're stuck with. And the classic example of this, which we also did last spring in 2200, is when you have a signal that you want to transmit from some source to some distant receiver, and the signal has frequency content in a certain place in the frequency domain, but the path from you to the receiver, from the source to the receiver, acts as a filter that filters out all that frequency content. So how are you going to get frequency content that's in one part of frequency space through a filter that processes frequency content in that part of the frequency space to zero? And the classic solution to that problem, the classic workaround, is amplitude modulation. And so that's what I want to talk about quickly about that, since you've all seen it before. And I know Peter Dorsha covered this when he taught 2200, and I'm assuming Lang Tong did as well. And I know that I did. So we're going to make quick work of it. And actually, I'm working on the Fourier Transform chapter of the monograph now, and just a heads up, in a couple more days I'll have that done, and there'll be a new draft available. And two things. It doesn't currently have anything about this amplitude modulation in it, but it's gonna. Okay, it's gonna have that. And also, I did a little more research on Parseval versus Plancherel. And it turns out that I had them reversed, that I read a bad website before, and so now I fixed that. So I had to go and change all the refs and labels and all that stuff. So anyway. Okay. So you're stuck with a filter. So here's an example. You have, say, an audio signal. That you want to send from a source to a distant receiver or whatever. And this is all happening on Earth. Okay, so we're not talking about like doing this out in space or whatever. And okay, so you have an audio signal. Now, an audio signal, note that say the signal is X, or let's not name it yet. The frequency content of an audio signal is where in frequency space? Yeah, 0 to 20 kilohertz, or if you do omegas, minus 40,000 pi to 40,000 pi. Okay, so the signal has frequency content. Is in minus omega in the interval minus 40,000 pi to 40,000 pi. That's relatively low in frequency space. It's way below megahertz, for example. All right, now you're on Earth and you've got this thing going. You've got this audio signal, and the audio signal is a priori an acoustic signal. But pretty much, you're not going to try an acoustic solution to this, right? You're not going to try, for example, turning up the volume really loud and hoping that the person out there in Pennsylvania can hear what's coming from Manhattan, right? You're not going to do that. Okay, everyone agrees. So acoustical solutions don't work. So cleverly, because you're ECEs, I guess the Schlumberger interview. Is it time? Good luck. All right. Acoustical solutions don't work. Oh, okay. Yeah. Acoustical solutions don't work. So what you do, because you're an ECE, you turn this signal into an electrical signal. You take a transducer. You take a microphone and you turn this audio signal into some electromagnetic signal, and you transmit it by electromagnetic radiation out of some antenna. So since you're an ECE, you turn the signal into an electrical signal, or an electromagnetic signal, let's call it X, and you transmit it through the air. But you can't just take the acoustic signal and turn it into an EM signal and transmit that through the air, because why? Because that signal X is still going to have frequency content in that relatively low frequency range. So this signal X still has frequency content in that low range. And the atmosphere through which you're trying to send the signal turns out to filter out electromagnetic radiation in that low frequency range. It's really good at passing high frequency electromagnetic radiation like cosmic rays and whatever, but really bad at passing low frequency. So filters these frequencies out. It essentially acts as a high-pass filter. Whose pass band is way out in kilohertz space, like hundreds of kilohertz space. So you've still got a problem. You've got a filter you're stuck with and a signal you can't send through it without further playing around engineering. So the solution to this problem is to take X and somehow piggyback it on a signal, let's call it Z, that does pass through the atmospheric channel and from which you can recover at least an approximation of the original signal X. So you quote unquote want to piggyback. And this, is this idiom familiar to everyone who's not a native English speaker? I just want to make sure. Because I read this editorial in the Sun today about like international students don't get enough attention for various things, and I was thinking, I wonder if when I use like cultural idioms and stuff that I'm not being appropriately attentive to, maybe people don't know them. Okay, all right, let's see. Manish, you be the one on top, and let's see who. No, just kidding. Blaj, you look athletic and low center of gravity. You can. No.
I don't trust them with my life. They live together.
I know they do. Yeah, I pass by their house every day on my way home. Yeah. All right. So what this means essentially is to put something on top of something else, and the something else carries it through. So you piggyback X onto a signal Z that, first of all, passes through the channel, and in this case I'm using the word channel to refer to the atmosphere, the filter that the atmosphere is or whatever, and from which you can recover X, at least approximately. Okay, so how do you do this? For this particular example, I'm going to whip right through it because you've all seen it somewhat before. Last spring I talked about the asynchronous demodulation. I'm going to tell you synchronous demodulation today and also throw in what the asynchronous is. They're both going to be in the monograph. So here's the procedure. You pick some omega c, and this is called the carrier frequency. And so carrier frequencies carry, you piggyback on top of something that has to do with the carrier frequency that's well within the channel passband. And you let z of t, let z have specification. Z of t equals x of t cosine of omega ct for all t. And what z of t is a cosine, a high frequency cosine, an omega c frequency cosine whose amplitude is modulated by x. And that's why it's called amplitude modulation. So z is an omega c cosine whose amplitude is modulated by x. And that's why it's called amplitude modulation. And it turns out that signal passes through the channel, and it's easy to show that with pictures. So let's use pictures to show why z passes through the channel. So suppose x has spectrum that looks like this. This is all too typical in a book. You always see they always use this because it's not square. And so this is your, say, 20,000, 40,000 pi, right? If x is an acoustical signal, an audio signal. Z of t is x of t times the cosine omega ct, and you can use Euler's formula. So z of t is equal to x of t times 1/2 e to the j omega ct plus 1/2 e to the minus j omega ct, which is 1/2 x of t e to the j omega ct plus 1/2 x of t e to the minus j omega ct for all t. Now, by the frequency shift rule, okay, z hat of omega is equal to 1/2 x hat of omega minus omega c plus 1/2 x hat of omega plus omega c by the frequency shift rule. So this is what z hat of omega looks like. Way out here in frequency space, at omega c, you're going to have a half-height replica of x hat of omega. And way out here in minus omega space, you're going to have the same thing. And the passband of the channel, by construction of omega c is well within the passband of the channel, so both of these spectra are well within the passband of the channel. So by choice of omega c, passband of the channel encompasses all the quote-unquote activity in z hat of omega. So z hat, or z, goes through. So we're bopping back and forth, I hope, comfortably between time domain statements and frequency domain statements. We look at the spectrum of z. We find the spectrum is in the passband of the channel. Therefore, the signal z passes through the channel, thought of as an LTI system. All right, so how do you recover x from z? It turns out it's really simple, although this is not a practically implementable thing. You just sort of redo the multiplication by a cosine at the other end. So at the receiver receives z, or a time-delayed version of z. It doesn't really matter, however you think about it. Like I'm forgetting about the fact that it takes non-zero time for a signal to travel from point A to point B, at least in the universe as we understand it today. So at the receiver, you have z. And processes it as follows. Takes z, multiplies it by cosine omega ct, same cosine that the transmitter used, and puts it through a filter whose frequency response I'm going to graph in a second, h hat of omega. And what's going to come out is x of t. H hat of omega is this. And remember, this is an ideal filter. You cannot build it. So this is at 40,000 pi and minus 40,000 pi. And height 2. And this is an ideal filter. And you approximate it if necessary. Or which is necessary. Approximate it as best you can. So this is where the word approximate comes in for the first time in this scheme. Why does this work? Why does this work? Let's give a name to this intermediate signal. Let's call it y of t. Okay. What does y look like spectral-wise? Again, by the frequency shift rule, y hat of omega is equal to 1/2 z hat of omega minus omega c plus 1/2 z hat of omega plus omega c for all omega. So this is what y hat of omega looks like. Again, you're going to have this gap frequency space. You take that picture and you shift it to the right by omega c, half the height, and you add it to that picture shifted to the left by omega c at half the height. And so way out here at 2 omega c, you have a 1/4 height replica of x hat. Same over here at minus 2 omega c. And in the middle, you have a half height plus a half height, which gives you a half height. Or a quarter height plus a quarter height, which gives you a half height. And here's your 40,000 pi. And from this picture, this is of y hat of omega versus omega. I claim it's pretty obvious that if you put y of t through a low-pass filter that has that frequency response, you get x of t out. What happens? That filter annihilates the part of y spectrum that's outside of plus and minus 40,000 pi, passes unadulterated the part of y spectrum that lies between plus and minus 40,000 pi. What comes out is just going to be x hat of omega in Fourier transform land, and therefore x of t in the time function domain. Okay? So that's a solution to this problem. It's quite a clever solution. And this is how AM radio, the basic idea behind AM radio. Now, as it happens, this technique requires something that's not practically implementable. And let's take the 3-minute break, and I'll go over that afterward. And if you want your exams, if you want your prelims and you haven't picked them up yet, I have them here. These guys reminded me that there was one question that I couldn't do, and therefore I figured it was only fair that I give everyone credit for it. And that was item 4 on problem 3. And Alex Spitzer, who's not here today, pointed me to a website that shows the following: that this condition fails for a rare bunch of numbers A, called the, it's some person's name, like McPherson numbers, Mackenzie numbers, something like that. But anyway, the lowest one known is, or the lowest one period is like 541. So the fact that I couldn't figure out whether this was true or not, I didn't feel so bad, because it's not true, but it's very rarely untrue. All right, so anyway, does everyone understand why this demodulation system works? As promised? Okay, so does everybody see why this demodulation system at the receiver puts out x of t, at least approximately? Is that clear? Because it's a really neat idea that someone came up with a long time ago.
Do you know when people came up with this?
No.
It just kind of seems similar to like the encryption scheme a little bit. Like you send something, maybe multiply stuff.
Yeah, in a very abstract way, it's definitely that. You know, you're whatever. Okay, well, what is wrong with this in a sense? What makes it, aside from the fact that the receiver can't build an ideal low-pass filter, what impractical feature does this whole scheme have? Alex? Yeah, they need to have a cosine that's exactly the same frequency and phase, exactly in sync with the cosine at the receiver has to be exactly in sync with the cosine at the transmitter. And that's very hard to achieve, especially if you have a bunch of, different kinds of receivers out there, you're broadcasting, say. And some people have good equipment, some people have bad equipment, that kind of thing. So that's pretty impractical. Okay, so a difficulty with this scheme. So this is called amplitude modulation with synchronous demodulation. And the practical limitation, aside from the non-existence of an ideal low-pass filter, is that it requires the transmitter and all receivers. I want you to be thinking here about like AM radio, it's a broadcast kind of signal, to have perfectly synchronized cosine generators. Same frequency, same phase, etc. The workaround is amplitude modulation with asynchronous demodulation. And this is how it's actually done in real life, approximately. So AM with asynchronous demod. Okay, so what's the approach here? The approach is that you make a different Z from the one you made in the synchronous demod. But the Z is still going to have those desiderata that it passes through the channel, and you can approximate, you can recover from Zx, at least approximately. So the key difference here is it's a different Z, and it's a different way of recovering X from Z. So for this scheme, instead of letting Z just be the product of X with the cosine, is you pick a little m, and this is going to be some number between 0 and 1. This is called the Modulation Index. So that, say, f of t equals 1 plus mx of t is strictly positive for all t. And notice that a priori you don't know that such an m exists, but it will exist if x is a bounded signal. X has to be bounded for this to happen. So such an m exists when x is bounded. So I'll just say x is in L infinity. Then you form Z as follows. Z of t equals f of t cosine of omega ct. And that's just 1 plus mx of t cosine of omega ct for all t. And again, you're going to choose omega c well within the passband of the channel. So omega c gets chosen the same way as before, carrier frequency. Okay, so what is Z? Z is a cosine plus mx of t times a cosine. So spectrally, it's going to go through the channel, as we'll see. But let's see what it looks like in the time domain. If f of t looks like this, say, versus t, and I always draw the same stupid picture, so I don't know why. So if f of t looks like that, and those of you who took 2200 last spring can go back and compare your notes and see how similar that looks. Nathan, you're laughing at it. Does it look very familiar? Pretty close, eh? All right, so if f of t looks like this, then this is what z of t looks like. It has, this is an envelope, and what's happening inside that envelope is a cosine going up and down like that. Okay, so that's what z of t looks like. It's still an amplitude modulated omega c cosine, but this time its amplitude is modulated by f instead of x. So z is an omega c cosine whose amplitude is modulated by f. Now, how do we recover x approximately from that z? It should be pretty clear from the picture. Certainly we can recover x from f if we have f, because f and x have a really simple relationship. right? We just take f of t minus 1 and divide it by m. So how do we recover f approximately from z? Essentially, yeah, remember, you're not going to be sampling because you're generating a continuous time signal. But if you just look at z, if you take your contacts out or whatever, glasses off, you could just sort of see f, right? It's like what the peaks are doing, right? So you can recover f from z by, quote unquote, following the peaks. And what that does is it leads the upper peaks. It leads to an approximation of f. And in turn, that gives you an approximation of x, where no synchronous cosine generators are required. You just have this incoming signal. I'll show you why it's incoming in a second. So which in turn yields an approximation of x. And just an aside here, why did we have to go through this whole m business? Why did we have to pick a modulation index so that 1 plus mx is positive and then use that f to modulate the cosine? Why do we have to do that? Any Victor?
If the signal you're passing through isn't, I mean, if that mx, 1 plus mx isn't always positive, can't you not necessarily read the signal from the peaks?
That's true. And the reason is, think of it this way. Think of it this way. If the upper envelope and the lower envelope aren't separated from each other, in other words, if they pass through each other, right, like this, which is what would happen if you didn't have a positive modulating thing, then when you were following the peak, you would say, uh-oh, when I get to 0, what peak do I follow now? If I follow the upper peaks, I might be following the wrong one. So just to have this recipe work, you need to have the modulation envelope be strictly positive. That's why you need the modulation index. Let's make sure that z passes through the channel. Z is equal to cosine. So z of t equals cosine of omega ct plus m x of t cosine omega ct. This cosine passes through the channel because its frequency is in the passband of the channel. So cos omega ct goes through because omega c is in the channel passband. What about the second term? The second term goes through for the same reason it did before. We already looked at what happened when you put x of t cosine omega ct through the channel. It went through. And so that one, m times it goes through for the same reason as before. So mx of t cosine omega ct goes through because same as before. Okay, so the bottom line is you form a different z. That z passes through the channel. The receiver gets that z. All the receivers get that z. And each of the receivers can have his own crappy peak follower. Some of them could be really good. Some of them could be really bad. It doesn't matter because all they're doing is following peaks. They're not multiplying by a synchronous cosine. Therefore, this scheme is a lot more practically implementable than the other. And this is amplitude modulation. Final gloss on this. You know, when I was in Massachusetts over fall breaks, there's this company that was in the news the last week or two because they bought some huge company. And I forget who they bought. But the company is called EMC. That's what people call it. But this is what their symbol looks like. It looks like EMC. with a 2. The reason I know that is because their headquarters is right near where my mom lives and my sister live. Okay? And they give a lot of money for parks and everything in Massachusetts. Has anyone seen this name of company? Okay, what do they do and who did they buy?
Oh, I have no idea. I just...
Dan.
Just
They do storage type stuff, data storage type stuff. So they're trying to, Dell bought them. They didn't buy Dell. Oh, that's right. Dell bought them. Dell is another Massachusetts. Is that what you're going to say as well? Yeah. Dell's trying to get into the Google Cloud kind of stratospheric, no pun intended, whatever. That kind of thing. So anyway. Yeah. Okay, so where was I? Oh yeah, one final gloss on this, and I think we've already moved the boards, so I won't move them again. Is the multi-user problem for this. So the multi-user problem, and that is that several sources want to use the same atmosphere simultaneously. We've only got one atmosphere, right? And therefore, you can't like wait for him to send his thing through the atmosphere and her to send her thing through the atmosphere before you send your thing through, especially if you're like doing something all the time. So several transmitters want to send their X's simultaneously using amplitude modulation, either through the same atmosphere. And clearly this is not a problem if one of your transmitters is in Point Barrow, Alaska, and the other one is in Pensacola, Florida. That's not a big problem. But if you're both in Midtown Manhattan, that is a problem, right? So how do they solve this? Solution is what's called frequency division multiplexing. And what's the basic idea of that? Anybody want to explain quickly, like what frequency division multiplexing is all about? Alex? Yeah, so there have to be rules, right? There have to be rules about who gets what omega C's. Like, I can't have my brand X Dave signal, pick my own omega C, and go rogue and send it out there. I have to, buy it or rent it or get it assigned to me by somebody, right? And when you assign these different users their omega C's, so everyone gets a different omega C. Every user gets its own, I'll try to use the neuter pronoun whenever possible, omega C. And the different omega C's have to be spaced out enough in the frequency space so that the individual users' Z's don't collide spectrally. Okay, so different omega C's need to be spaced far enough apart so the different user Z's, in either case, if you're using synchronous or asynchronous demodulation, don't quote unquote collide spectrally. And I hope you understand what I mean by that. If you graph the spectrum of the Z's, it's always going to have two little pieces of X or something like that out there. Two little replicas of X of half the height, or maybe with a cosine thrown in if you're doing asynchronous demodulation. And if you assign a user's carrier frequencies too close, the replicas of X are going to collide in in omega space. And that's what I mean by collide spectrally. So you want those omega C's to be far enough apart. And that's where the FCC comes in. You know, they regulate the assignment of carrier frequencies for AM radio transmitters in given markets. So in New York City, you know, I grew up in New Jersey, so, you know, you look at the AM radio dial, and it was always started with 540, right? And then there was like 660 and 710 and 770. And I think there was actually 740 in there as well, 880, 990, 1010 wins, blah, blah, blah. You know, all these kind of things. If you look at those numbers are kilohertz. Okay? Like, this station has carrier frequency 660 kilohertz. This one has 770 kilohertz. And if you look at the spacings, you'll discover that 710 and 740 are seemingly too close. And the reason they're not too close is because instead of using what's called this thing, which is double sideband amplitude modulation, the actual way they do it is single sideband, so you only use half the spectrum. But the rest of them are pretty far apart. Okay, so you've all seen this before a little bit, in EC 2200, but now you see it in the context of this class. Yeah, David.
How come the method for listening to it where you follow the peaks, how come that only works for asynchronous? It doesn't work for it doesn't work for the synchronous one?
Because in the synchronous one, you're going to have this kind of a situation. Suppose that X looks like this. Say, I'll do it like, suppose X looks like that. Then the Z is going to look like this. I'm going to dot in the envelope here. It's going to be like this, right? This is what the Z is going to look like. Now, you tell me, if this Z comes in, give me a recipe for following peaks to get X. Yeah, exactly. Yeah. So I can't just say follow the upper peaks, you know. Yeah. Okay, any other questions about this? All right. So now I want to start, and in the last 3 minutes today, I'm not going to give you very much, but I want to talk for a couple of days about wavelets. And we're just going to be scratching the surface on this because it's a huge field and it's really current and whatever. So I guess in the limited time today, I'll talk about one. I want to open the discussion by saying why. Why do people care about these things? Why is wavelets this hot area of signal processing study, all that kind of thing? Why? Wavelets really is sort of just another way of doing Fourier analysis in a sense, because what you're doing, it turns out, you're going to have a complete orthonormal set of signals, and you're going to be expanding L2 signals in terms of them, just like we did for periodic signals in Fourier series. The thing is that these are going to be different things you're expanding in terms of. Why would anyone ever want to do that? What's missing from Fourier analysis, Fourier transforms, Fourier series? All right, so here's one which I think is a very compelling example. We talked about the finite duration A440, right? The finite duration A440 has a spectrum that looks like a sinc function. At least that's the magnitude of it. And it's going to have some phase. And the phase is going to depend on when in the signal that finite duration A440 occurs. Okay, if someone plays a finite duration A440, say a 3-second A440, from time minus a second and a half to time positive a second and a half, it's going to have a spectrum that looks like a sinc function. Suppose someone plays that same 3-second A440, but 10 minutes later. What is the magnitude of its spectrum going to look like? The same, because of the time shift rule. All the time shift rule does is it tacks on an e to the minus j omega t1. That has magnitude 1, has no effect on the magnitude. If the person plays it 10 hours later, same thing, except t1 is going to be bigger. Bottom line is that if you're given the Fourier transform of a signal, you're generally given a picture of its magnitude or some kind of data file containing magnitude values, and a picture of some kind of data file containing values of the phase. Any info about the timing of a finite duration A440 is buried in the phase. It does not affect the magnitude at all. And in fact, if you take a musical piece that contains certain notes of certain durations, and you take those notes of durations and you shuffle them up completely, like John Cage might have done, right? And you make another musical piece that has the same notes with the same durations but happening at completely different times, the magnitude of the spectrum of the signal corresponding to that piece is going to look exactly the same as the magnitude of the spectrum of the signal of the original piece. All the info about the timing of those various notes is buried in the phase. Okay, so first issue is, are we able to resolve that phase to figure out the timing? And it turns out that the longer the gap between notes, the harder it is to do that, because the phase is going to be, you have to essentially figure out the derivative of the phase. Anyway, that's the first thing that's missing, and that's one of several. So hoping to motivate it.